Okay, so remember this unit is going to it's going to leave behind what we did before, and this is more like the quantitative side of chemistry. So we are going to look at how much energy is released or absorbed by a reaction. We're going to look at Okay, so this note is just sort of the theory behind the calculations. We'll do one quick calculation at the end, Q equals MC delta T. So in physics, you might have looked at heat transfer. So that's really a really simple way of looking at it. We are going to look at what happens when then you put that substance in a reaction, or you change the substance's state, how much energy is released or absorbed. So the study of energy transfer, dynamic usually means something is changing. So thermodynamics is looking at the study of energy transfer. So we're going to talk about physical and chemical changes a lot. Nuclear reactions we'll talk about in 5.1, but obviously we can't do nuclear reactions in our classroom. So we're going to focus on physical and chemical because that's much more practical. So when, again, thermochemistry, the study of energy changes, and physical changes are a change in the arrangement of a molecule. So the energy value is the lowest because they release or require the least amount of energy. We could put an ice cube on the table and it would melt at room temperature. Yesterday, we saw the alcohols evaporate without any input of energy at all, versus chemical. So chemical has a wide range. There are some reactions that you get a very small temperature change, whereas some, like in your car, that obviously gives off a ton of energy, makes the car go. You can travel for kilometers and hours. And then nuclear reactions, of course, can blow up cities, right? So nuclear reactions are very different from chemical. You're actually changing the nuclei or getting new elements. So we talked about in Structure and Properties, different scientists who discovered that atoms can decay or break apart and make new elements, which is nuclear fission, which is the reaction that occurs right now in the nuclear energy reactors of the world. We're trying to make a reaction a feasible, efficient nuclear fusion reaction where they come together like on the sun, because that does not release radioactive waste, which is of course a criticism of nuclear reactors. But again, so, for the sake of your unborn children, that we're not going to do nuclear reactions. We're not going to blow up the city or change anybody's DNA or anything like that. Okay. So you may have heard of the laws of thermodynamics. Again, this is actually, and even in biology, you would talk about energy transfer as well. So what we're going to do is, and the easiest thing to do is look at how fast particles are moving. And how do you measure how fast particles are moving? You use temperature, which we can easily measure in the lab. So how much energy does a particle have based on how fast it's going? The hotter something is, then it has more energy, and usually it's going faster. The slower something is, the less energy it has, and it feels colder. This symbol here means change or delta. So energy cannot be created or destroyed. This is the first law of thermodynamics. Wouldn't it be wonderful if we could create energy from nothing, or have like a perpetual motion machine where it just picks up energy without any input? Those kinds of things do not exist. Energy can, however, be transferred. So as humans, we have definitely taken advantage of that. We plug things into outlets converting electrical energy into light energy, into sound energy. We eat chocolate bars. Our cells turn that into those bonds, breaks them apart and makes the ATP, changes it into chemical energy and heat. When you go running, then you often feel warm and your body is losing some of the energy provided by food as heat. Okay, so one of the things that we're going to look at, especially for when we do 5.2, is looking at trying to contain a system in a surroundings, because we are going to, this is chemistry, we're going to focus more on what's the energy that comes from bonds breaking or bonds forming. So it's difficult to stick our thermometers in between the atoms when they're reacting. So what we can do is put the system, whatever it is, in something, surroundings, and measure that temperature change. So we, in our class, we usually use distilled water. It's easy to measure the temperature of water. If you continue and take upper year chemistry courses, you might use a calorimeter that you can actually set fire to things inside the calorimeter, and then you measure the temperature change in air. So air is also easy to measure the temperature change of. So we want, the system is the reactants and products, or products that are reacting or changing state. And then the system is contained in the surroundings. And what we don't want is much interaction with the environment. So we can do a simple lab with coffee cups, styrofoam unfortunately, but that's a good insulator. If you keep the cups closed, the system and the surroundings are in the cups and not interacting with the classroom environment. And hopefully we'll get to do the Hess Law Lab. Kids actually get like very, very small percent error, 0.6%, 1%. So you can easily prove these laws. So we want to, if you're going to try to measure the energy from a reaction, then you need a closed system versus an open system. Like if we did the reaction in a beaker, beakers don't have a lid. Even if you try to use a watch glass, they have that spout. Energy can get in or out. That is difficult to measure. So normally we would not use open systems at all. So we're going to use a calorimeter. So calorie is an imperial measurement of energy. We're going to use joules and kilojoules to be metric, but meter measures, meter measuring energy, okay? So there's a variety. Like I said, we can use coffee cups and it works really well, no problem. So when you are going to break bonds, that always requires energy. When you create bonds, that's going to release energy, and then it's either the breaking the bonds and requiring energy is greater than the amount of energy released, or the amount of energy released is greater than the amount of energy required. And that is the basic difference between endo and exothermic. So one of the big things about this unit is deciding, does a reaction release energy? Does a reaction gain energy? And it's 50-50. So it talks about the net. So let's say you have a job and you get whatever, $15 an hour. Then you work 10 hours, 15 times 10 is 150. That is not usually what goes in your bank account, right? That's your gross pay. Maybe you have union dues, maybe you contribute to CPP, EI, whatever, or you have to pay for your uniform or something. Then your net pay is what goes in your bank account, so subtracting all the deductions. So what we're going to deal with is overall, and we're going to do the calculations for this, does a reaction require or absorb energy or gain energy, or does the reaction release energy? So one of the ways, if you like a trick to remember these things, releasing is like exiting, so it exits, so exothermic. If you don't like that, that's fine. But it's really important. So endo is absorbing or gaining energy. Exo is releasing or losing energy. In biology, they call it endergonic and exergonic. It's the same thing. The same basic principle. Okay, so this chart here, so in the reactants, bonds have to be broken. In the products, bonds have to be formed. And there's two spots, right? One's endo and one's exo. Energy, if you break bonds, energy is always absorbed. If you form bonds, energy is always released. And then you're just looking for which one's greater. So if the energy absorbed is greater than the energy released, then that's endothermic. We say the system absorbs energy, or the system gains energy. If you don't like the word absorb, that's fine. Okay? And then the reverse is true. So reactants, bonds still broken, products, bonds still formed, but the energy released is greater than the energy absorbed. Say the system releases energy and it's exothermic. So because we're dealing with changes that actually require both kinds of energy, both energy released and energy absorbed, then we call the change, the relative change, we call it enthalpy. But we use, to differentiate it from energy, we call it delta H. So in this unit, we are going to calculate the net absorption or release of energy in a bunch of different ways. So today we're going to do, or in the afternoon, we're going to do using calorimeters. Then we're going to use Hess's law. We're going to use enthalpies of formation. So this word enthalpy just means, it's just basically looking at the study of the energy change. Does the reactants absorb more energy than the products release? Because there's actually a lot going on here. So if you think about a bond, some molecules are bigger than others and the reactions are just faster. So we talked about that, and even in grade 11, like the trends in the periodic table. Some elements are more greedy for electrons. So enthalpy basically is taking all that into consideration and looking just at the energy. How much energy am I going to need to put into this reaction? How much energy am I going to get out of it? So physical changes, if you want to write in some examples, any change of state, I think it just says examples there, yeah. If you prefer like melting, boiling, those are changes of state. Another big one that people sometimes don't remember is, as a physical change, is dissolving is a physical change. You could evaporate the water and get the solid back. Physical changes both release and they absorb energy, but it's on a pretty small scale. So you could melt an ice cube at room temperature. You could, put alcohol on your hand and watch it evaporate, and you wouldn't worry about burning yourself or anything like that. So they are the weakest. They have the smallest energy range. And what happens is, this is a graphical representation of what's going on when you break intermolecular forces. So, like I said, we are going to measure temperature, okay? So whatever solid you have, starts at a solid, yes? And then you turn on the energy. So turn on the stove, turn on the Bunsen burner. You're continuously putting in energy, more and more energy. So what happens is the particles start to move faster and faster and faster. Their temperature increases. And then you get to melting point. So melting point is the change from solid to liquid. And there would be this plateau where you're still adding energy, but the particles are not changing in temperature. So at the plateau, that energy is being used to break intermolecular bonds. So plateau, that's level, like where they're straight, okay? And then, so every change of state, once you get past the melting point, once they're far enough apart, then you keep adding energy. They're moving faster, 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 moving faster, faster, and then you would get to boiling point. And then there would be a plateau again, where the energy is being used to break the bonds in the liquid to make a gas. So when I was in grade 12 chemistry, we had to watch an ice cube melt and measure the temperature changes as it went along. It was very thrilling. Miss Vakanko was my chemistry teacher. Okay, so then chemical changes. Like I said, there is a wide range because there is a wide range of chemical reactions. So very common ones that we're going to talk about in this unit, combustion, because obviously as humans we burn a lot of things. Some things we shouldn't, but we do it anyways. We also, neutralization is an easy common reaction to do. And the Hessel lab, we're going to do single displacement. So if you want to write that in there, you could do double, you could do whatever, but we're going to do single. Okay, so this time now you're actually breaking the chemical bonds, which requires more energy. They are stronger. And this occurs in our bodies, in the environment, everywhere. So very important. And then nuclear changes, again, changes in the nuclei of atoms. So these are the forces holding a nucleus together are obviously very strong. So then if you have an element that will decay, then that's going to release a ton of energy. So, and if you look at Einstein's theory of relativity, he says that mass in a nuclear change, mass times the speed of light squared can actually be, you're converting mass into energy, which is an incredible amount. Can blow up cities, can't kill tumors, etc. Huge amounts of energy. We're not going to do any calculations with this. Like I said, nuclear reactions are fine, but they're just not practical in a chemistry experiment. In the one video we watched, the guy said chemistry cares about the movement of electrons, right? So you're changing the nuclei, that's a whole other branch of science. Okay, so heat, we're going to use the symbol Q, and it refers to the transfer of kinetic energy. So if something is hotter and is moving quicker, then it can collide with something else and transfer energy to it. We're going to use joules or kilojoules. We're going to use metric units. I am not going to ask you to convert between calories or kilocalories and joules. And then heat is transferred spontaneously from a warmer object to a colder object. And I feel like this is a good life skill. If you've ever touched something hot and burnt your hand, that's what's happening, okay? You're subject to the laws of thermodynamics. Temperature, we're going to use capital T. In the rates unit, it's going to be little t for time. So try to use capital T. So again, temperature is a measure of the average kinetic energy. This does cause some problems. If you think about like a boiling pot of water, the steam's at the top. Those particles are moving quickly, whereas the water is like near the bottom is starting to heat up. Okay, let me just finish this. So we're going to use degrees Celsius. We don't often have to change to Kelvin, not till the equilibrium unit. And then to calculate heat transfer, we're going to use this formula all the time. It is going to be very important that you do final temperature minus initial temperature. That is going to help us decide whether it's exo or endothermic. Okay, so this slide is important. Again, Q is heat. Specific heat capacity is, this is a reference value. So if you have a textbook and somebody has put a sticky note on page 301, 306, 307, leave those in there because there are reference values. So specific heat capacity is how much energy it takes to change 1 gram of something by 1 degree Celsius. So the more energy it takes, the more resistant the substance is to energy change. And the units used are joules per gram degree Celsius. Okay, so a simple question. Oh, just read through this, and then when you come back, we'll do 5.2. Have a good lunch.